Whether oil or copper, either you have it, you can get it, or you don't. And if you don't, you do not get to play. Early conflicts over materials were not so much imperial or national, as there were no empires or nations to speak of. Instead, such struggles were about clan, tribe, and family. There also wasn't a lot to fight over. In the Stone Age, it wasn't like you had to go that far to find stone. Sure, there were certain rocks that were better for cutting or arrowheads, but the tyranny of transport limited everyone's reach. We were far more likely to fight over food and land that could grow it reliably than rocks. Copper was nearly unique as a material in that it is one of the few materials that on occasion can be found lying about in its natural metal form. That never happens with iron. Iron ore on its own is useless, and the art of turning the ore into actual iron required hundreds of someones who knew what they were doing. Most governments were more likely to launch attacks to abduct blacksmiths than to secure iron ore or copper mines. Going back dozens of centuries, we had been limited to copper, lead, gold, silver, tin, arsenic, iron, and zinc. With the codification of the rules of chemistry and physics, we expanded that list to include cobalt, platinum, nickel, manganese, tungsten, uranium, titanium, chromium, tantalum, palladium, sodium, iodine, lithium, silicon, aluminum, thorium, helium, and neon. Consequently, now we have everything from flamethrowers to steel that won't melt if exposed to said flamethrowers, to meshes of copper and gold and silicon that can place more brain power in one hand than the entire intelligentsia of the medieval world, to party balloons. Every material has its own use. Every material combined with others has more uses. Some allow substitution. Whether used in construction or war or urbanization or manufacturing, they require industrial-age technologies to be produced, shipped, refined, purified, alloyed, and rearranged into value-added products. Should anything happen to the sustainability or reach of the industrial technology set, all of them will simply fade away. Poland became Europe's premier power due to the income from a single salt mine, salt being the only reliable method of the 1300s for preserving large amounts of meat or fish. In the late 1800s, Chile warred with Peru and Bolivia over the Atacama Desert and its rich deposits of copper, silver, and nitrates, a key component in early industrial gunpowder. Britain made a bad habit of sailing anywhere, at any time, to attack anyone who had anything the Brits might fancy. The Brits were particularly fond of seizing access points like Manhattan, or Singapore, or Suez, or the Gambia, or the Irrawaddy. World War II was in many ways a fight over inputs. Most of us have at least an inkling of the strategic competitions that took place for agricultural land and oil, but battles over industrial materials were just as front and center. Post-war, the French spearheaded the formation of the European coal and steel community in an attempt to resolve the same iron ore here, coal there problem with diplomacy instead of bullets. Among the many reasons the Japanese conquered Korea in 1904 to 05 was for timber for use in construction. The subsequent Japanese expansion into Southeast Asia is often and accurately billed as an oil grab. But the home islands weren't simply energy poor. They also lack other central industrial materials that could only be sourced by physical expansion, ranging from iron ore to tin to rubber to copper to bauxite. In all cases, the dominant technologies of the age demanded that every country either have sufficient access to all these inputs and more, or be lorded over by others. That suggests the materials competition of the future will be far more wide-ranging and multifaceted, while the fallout from failure to access such materials will be far more damning. Nor are any of these industrial materials evenly distributed across the globe. Each has its own geography of access. It's easy to draw some dotted lines based on likely trading zones and envision an Africa that has access to the inputs for electronics, but not steel. A Europe with nuclear power but no green tech, or a China with old-timey batteries but lacking the capacity to transmit electricity. This will be a struggle for everything that is required to maintain a modern system. As such, every tool will be on the table. Some will attempt this for that trades. Others will be more energetic in their efforts. We're going to focus on the top 15 in terms of international exchange. Hopefully, that will sufficiently map out our present so we can glean some glimpses of our future. The story of today's industrial materials is the story of mass industrialization. China has become the world's biggest importer, consumer, and processor of many of them. The world will survive China's fall. The world of industrial materials will survive China's fall. But many of the bounces will hurt. As the industrial age has matured, and as industrial materials have become more numerous, discrete, and specialized, the geography of their production and processing matters far more now than when you could simply scrape up some copper during a stroll through the woods. Beginning roughly in 1980, the human condition launched into its next technological era, the digital age. Mass digitization could not have happened without mass industrialization. It is industrialization that has enabled us to identify, locate, mine, refine, and purify the materials that drive modern society. Many parts of the world are on the verge of deindustrializing. It is this looming inadequacy and incompleteness of access that will rive the world apart. History tells us we may be on the verge of a series of massive breakthroughs in material science. The in-progress demographic bust threatens to reduce the human population writ large over the next few decades by as much in relative terms as the Black Death effect. No matter what specifics the future holds, we will all need to get by with fewer workers. Our history strongly suggests that fewer workers by definition means more expensive labor. That in turn should prompt everyone to figure out how to make that scarce labor more productive. The first material is arguably the most important since it is the base material that makes everything from buildings to roads to telecom towers possible: iron ore. Regardless of variety or quality, iron ore comprises at least the majority, and often more than 90% of the material in every bit of steel humans use. This makes understanding the world of iron ore very simple. You just need to understand China. China sits squarely in the intersection of two quintessential trends of the modern age: rapid industrialization and urbanization on one hand, and China's trademark hyper-financing on the other. Any successful industrialization and urbanization requires new roads, new buildings, and new industrial plant, all of which require massive volumes of steel. Hyper-financing can help make all that happen, but in doing so, it overbuilds everything. Not just the roads and buildings that mean yet more steel demand, but also the industrial plant that is used to make the steel in the first place. China's industrialization push has proven so huge and so fast and so overfinanced that China isn't simply the world's largest producer of steel. It regularly ranks among the world's top 4 importers of steel, particularly the product sets on the higher end of the quality scale. But that overfinance also means China produces steel with zero regard for the reality of domestic needs. And so China is also the world's largest steel exporter, particularly steel product sets on the lower end of the quality scale. All that requires a world full of iron ore. China isn't just the world's largest importer of the stuff. It doesn't simply take in more than the rest of the world combined. China imports more than the rest of the world combined times 3. China is the global iron ore market. As to production, Australia exports half of global iron ore volumes, with Brazil exporting half the remainder. Unsurprisingly, China gobbles up nearly all these southern hemispheric powers' exports, as well as additional big chunks from Russia, India, and South Africa. Nor is China the only country that uses steel. It is just the only country where the economics of steel are so fundamentally out of whack. Most everyone else uses iron ore produced a bit closer to home, or in many cases at home. Their balances are rounded out by the very big business of steel recycling. Roughly 1% of buildings in the advanced world are torn down every year, and every scrap of steel used to reinforce them is melted down, reforged, and given a second life, or third, or 18th. This duality between the ravenousness of China and the rather placid pace of steelwork everywhere else makes the forecast rather straightforward. The vast bulk of the world's iron ore production comes from countries that face limited to no security threats as the world deglobalizes. In descending order, Australia, Brazil, India, South Africa, Canada, and the United States. The countries that export the vastness of global steel. In ascending order, Ukraine, Germany, Russia, Korea, Japan, and above all China, are somewhere on the sliding scale between facing severe complications and utterly screwed. The world is going to have massive shortages of steel at the same time that the supplies of the raw material to make that steel will overflow. The solution is simple. the world will need more smelting capacity. But it is critical to understand that not all steel is created equal. Unlike most materials, all steel is 100% recyclable. But recycled steel is not the same as virgin steel. Think of steel as if it were a sheet of aluminum foil. Then crumple it and smooth it out. Hell, try ironing it. Then rinse and repeat. Recycled steel is just as strong as virgin steel, but it cannot be made as pretty. So, recycled steel is used in rebar and I-beams and auto parts, but fresh steel is used in exposed applications you can see, such as appliance cladding and roofing. First-round steel is made with coal-powered blast furnaces to up the carbon content, which makes the steel stronger. The process is extremely carbon-intensive because, it uses coal. Also, steel forging demands not just any coal, but a coal derivative that's had its impurities burned out, called coking coal. Somewhat similar blast furnaces can also handle the recycling, but a far more efficient process is to use something called an arc furnace to run a current through scrap steel and literally electrify it until it melts. That means the best economics for recycled steel involve not simply physical security and proximity to the raw inputs, but also cheap electricity. The winner on all three counts will be the United States, with America's Gulf Coast looking the most promising, for the triple reasons of having great electricity prices, plenty of greenfield industrial space, particularly at potential port locations, and proximity to both large local and regional markets. Think Texas, the East Coast, and Mexico. Add in ample coal supplies, and the Americans could get into virgin steel production too. Secondary locations that look very favorable for steel recycling include Sweden, hydropower, and France, nuclear power. Australia has a wonderful opportunity to surprise to the upside and move from the low-value business of digging up ore to the high-value business of forging virgin steel. All the Aussies have to do is bring their iron ore and coal together from where they are produced on opposite sides of the continent. Put up an army of solar panels and wind turbines throughout the sunny, windy outback, and the Aussies could recycle steel on the cheap as well. Outsized success in these four countries might not sound like enough to maintain global steel supplies at the current level. You're right, they would not even come close. But we're not kicking around that option as feasible or even necessary. A world without China needs less than half as much of the stuff. And that's before considering the likely far slower paces of building and industrializing that will define the future world. Another material integral to all things in the modern world is bauxite, the raw material that gives us aluminum. The aluminum refining process is pretty straightforward. Strip mining produces bauxite ore, which is then boiled in sodium hydroxide to create an intermediate product called alumina. This cocaine-white powder has a variety of uses in ceramics, filters, body armor, insulation, and paint. Some 90% of alumina is then in essence electrified Jaws 2 style until it becomes aluminum, which goes on to be molded, bent, and extruded into everything from airplane and car parts to soda cans to frames to tubings to casings to machinery to wires. Pretty much anything where low weight and or low cost conductivity is a primary concern. Assuming you begin with decent quality ore, 4 to 5 tons of bauxite becomes 2 tons of alumina becomes 1 ton of finished metal. Bauxite mines and the alumina processors are owned by the same firms, while aluminum smelters are completely different entities in different countries. China has long since mined itself out of its high-quality bauxite reserves, and is now left with a dwindling supply of low-quality mines whose output requires much more filtering and much more power to provide much less end product per ton of ore. That has turned China into a voracious importer of bauxite from everywhere. As of 2021, China absorbs 2/3 of all internationally traded bauxite, while smelting about 3/5 of all aluminum. In true Chinese fashion, the majority of China's aluminum output is almost immediately dumped on international markets. This is both great and awful. It's great in that it simplifies understanding of the supply chains. It's awful in that the global supply chain for one of the world's most utilized metals is wrapped up in a failing system. When China cracks, the world will face global shortages of aluminum, as there simply are not sufficient smelting facilities elsewhere to cover more than a few percentage points of the pending shortfall. The problem isn't so much access to bauxite. The stuff is sourced in countries that will be broadly okay in the post-globalized system. Australia produces more than 1/4 of the world's exports, with Brazil, Guinea, and India kicking in another 1/10 each. No, the problem's power. From shovel to final metal, electricity counts for roughly 40% of the total cost. And that's a statistic that takes into account the fact that in most places that smelt, power is ridiculously cheap and/or heavily subsidized. Countries with ample hydropower, Norway, Canada, Russia, are big players. Such a restriction limits the wheres for siting new smelters. The biggest new player will be an old player. Courtesy of the shale revolution, the United States already has the world's cheapest electricity. Add in some of the world's best green tech potential, and power prices in large portions of the country are likely to go down in the years to come. The biggest competitive advantages will likely be felt in Texas, where the shale-related and green tech power generation trends overlap, with plenty of port capacity to site a smelter. Or 5.
Norway's ample hydro capacity, combined with its location just above a mainland Europe that can produce about 1/3 of its needs, argues for massive Norwegian expansions. Luckily, for everyone, aluminum recycles very easily. In Europe, capture programs are enough to supply 1/3 of demand.